Anytime I stop this thing, these two are doing the same thing. But this one is trying to be globally symmetric and anti-symmetric result is practically no motion at all. It's a little bit in the global direction, which is radial for it. Whereas these guys up here, let's erase 0 and erase, well, I'll leave the lines, they don't hurt. This guy right here, this one is globally anti-symmetric. Let's see, this is kind of the minus of that. This one isn't moving much. A little bit of motion in the anti-symmetric direction. But when this one's on the outside, that one's on the inside, and vice versa. Same with those. Okay. But they're all locally symmetric, and that just means radial. Pretty close to radial. You start raising this constant here, so they can couple more. You destroy the local.
Those are not locally symmetric.
This is locally symmetric.
But the ones that are in this axis.
And this one is too.
But in this one, I mean in the horizontal.
Oh, this one here?
That's not locally symmetric.
It's trying to be both. You see? Can't do it.
So it's neither.
It's wiggling a little bit because that's the extent of what this very small coupling, the spring between all of these is so small. There should, that's something we've got to draw it right. It's got to be there so people can see. The string is not showing.
Well,
K1.
Okay, well I got to put a minimum on it because
Yeah.
it renders as long as you make this spring strong enough.
It's got to be a floor to the rendering. Yeah. If I turn it up, just for the heck of it, we'll do that. Let's pause this thing. Locally. I can turn up the K1, nearest neighbor, right here. Let's just jack it up a tiny bit.
If you're wanting just a bit, you can put your cursor in there and use the up key.
Yeah. I can
also on there or on the keyboard.
Yeah, I'm so used to those old OS 9 controls where you could easily think, if I make it 0.1, that ought to be enough to kind of screw it. So let's see what it does with logic. And let her go.
It's zeroed.
Oh, it zeroed it out. Okay, we were working with this one right here. Let's let her go. See what happens. Now you can see the string. And you can see this one's starting to move now. It shouldn't move at all if it was being local and global, but it's only being global. The local's starting to disappear.
That's what the 0 says, right?
Yeah. I'm surprised it doesn't have a little bit of motion this way too, but it seems to be picking. It's being treated to the effect of some of these things which are very locally anti-symmetric. So I guess it's not unreasonable it would favor that. And then I'm going to 0. I'll leave those lines.
The algorithm
this
considers those motions to be small so that the angle between the sides
This one will be
change.
globally anti and locally symmetric, I hope. And you can see the little error there. It's not following the absolute symmetry of this. Pause. So this is again globally anti-symmetric. this thing's in, well, this one's out.
Right-click on the molecular plot and you can change the springs on the fly.
Right click, okay,
On the molecular plot.
on this part.
Yeah.
Okay, I'll just do it right there. Oh yeah, here's it, that's good.
And you
That's
could
it.
just stick it in your up arrow key as well, and it'll just slowly evolve.
Yeah. Let's see if
Hold your keyboard arrow key down and it'll just sail away.
that- oh, I did the wrong one. Go ahead. But it's interesting, this is, you can see the eigenvalues change as you
Yeah.
do that. That's a nice feature. We didn't have that before. I certainly don't have it in OS 9. That's a good feature. Gives you a nice feeling for what's going on there. Let's just try one that's not too out of the way. That's a pretty good set of bands right there. They're kind of symmetric, so let's
You can see the
return.
nearest neighbor springs much better now.
And resume.
So now when you changed that, it zeroed it,
Yeah, we
because
got
you
it.
changed your model.
Let's try one of these things that's supposed to be not moving. Well, first of all, this one is still maintaining the local let's see if that's right, local symmetry. This one's 0. It's right in the plane of that rotation axis, but because this is opposite, it shouldn't be doing anything if the coupling was weak. The coupling's very strong now. K1 is almost 2, okay? So this thing is neither symmetric nor anti-symmetric. It's cockeyed. It's close to being anti-symmetric, but it's not. It's what it's supposed to be, is locally anti, but it's not. Anyway, that does that help make sense of things? This is just Newton mechanics, right? But a lot of the features that you get with the quantum mechanical are shown just with this 6 degrees of classical freedom. That's a lot of degrees of freedom over there. And that's sort of a cheat, because basically what I'm doing here is I'm making a wave out of about 48, or I don't know what it's set for right now. You can set it up to about 128 coarse grains. And you can make the well really square. This shows you, because we're making a Fourier transform of our square wave, it's got the ringing in it. And I left that in there because I want you to see that it's, you know, how the potential is being built. And you're just changing the spring constant of a bunch of oscillators. That's all you're doing.
Can you put the wave that one is making?
This one,
On there.
that would be a mixture, I guess, of this one and this one,
Mm-hmm.
or a mixture of this one and that one. What do we got here? Yeah, we're doing the outside guys, right? Let's see what happens. It's a good idea. What do I got going right now? Oh, I've got an E going right now, so I'm going to kill that and start these two just to try that. Does that sound like a good idea? I'll zero
It's because
this.
I wanted to see how the waves look,
Yeah.
and how that one
Okay,
looks at the
here's
same time.
this
so-
guy right here. All it does is rotate, and then I add to this thing right here, and I make a Lissajous pattern. Very non-stationary. Now, if these two energies, this one 0.92 and 1.47, were they're rational. They're pretty rational. It's pretty rational. But you can see it's not perfectly rational. It's starting to close up, right? So if you do a continued fraction of 147 and 092 ratio, you do a continued fraction of that, looks like you'd get a couple of big terms to start with, which would correspond to 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 6, 7, 8, 5 to 8. You're getting a 5 to 8 ratio here, but it's not quite 5 to 8. So the next term in the continued fraction is very small. You can see that it's hanging in there with the original 5/8. So it'd be, next stop would probably be something like 2,000 or 10,000 to some other, 10,017 to, 10,018. That's
So-
a little bit extreme.
At some point, those are going to be squares, right?
Oh,
It's starting to close up.
and that's what you get with respect to the symmetry axes, remember? When you did the A-D type of resonance, when you talk about A and D, right, you got a square. It's when you did the B and got the thing on the 45
Yeah.
that you get what most people think of as a resonance, the B type. And then in between that is A and B, right, where you have a rectangle that's tipped at some arbitrary angle. And this is all perpendicular to C. We don't have any C here at all because this is standing waves. You get C with these guys. So then you get, polarization that changes from ellipse to ellipse. We can do that pretty easily. This is kind of neat right here. It's just about to finish here. Close up. And what you're seeing is the outline of a curve that we started with. And now it's gone. Yeah. Okay. Let's go ahead and 0 the amps. And I'll try some tricks with these guys right here. Better erase though.
Oh yeah.
Let's try
90-degree phase.
this guy first, just to see what he does. We got a weird mixture of global and this is symmetric, that's anti-symmetric right there locally. And then I add to this, let's just add to this one down here. And that's quite a splitting, 141 to 116. That's quite a splitting. We're getting quite a beat out of this. We're mixing opposite pairs. I'll try to make their amplitudes about the same. This is a weird one. This one's
Oh, you
already
know what I
close.
noticed? Remember when you show us when we had like the two pendulums, those in the opposite things are doing that. See
Mhm.
one, and then the other. See?
No, that's true. You're going through a variable
It's like
ellipsoid.
conservation of momentum is in that axis. See
In a
what-
sense, yeah. The size of this thing is not changing. I'd have to add a third level to make that happen. Yeah, there's some advantages to having this really simple analogy to that, because that was so many things going on here. Here you just have 6 times 2 is 12 dimensions, right? It's already a lot, but it's You dare I throw in a little bit of that?
Yeah, we
don't
need a
think-
global amp slider again,
Yeah.
just to pull it down so it's
Yeah.
easy to visualize.
Now that when you start doing topological properties, then you would like the actual frequency of this to be, you know, kilohertz, and you would just adjust parameters and watch the whole forms, you know, change and turn inside out. Because these really are four-dimensional objects, each of them.
You know what's funny is, see those three that are very chaotic now. The pattern just lost.
Yes.
Because I mean, if you see like those three right now, and see the other opposite three start doing what the other three were doing, and now at some point these three are going to do. See, this.
That is, yeah. We ought to start over, because the blocks are blocking
Like,
from the previous
when you
calculation.
ratchet the end up, you'll
I'm
find
just
all
going to go
sorts
ahead
of
and
little
go
interesting
erase.
There
subfamilies.
There
must
we
be
go.
something related to the group theory. Why this group of three and the other group of three, they kind of like do this, follow this pattern.
Subgroups, perhaps the subgroups will give it to you.
It's
Cosines.
really hard to second guess. You put three things going, it's already a mess. As they say, two's company, three's a crowd.
Let's see.
So we got a crowd here, right? And they're just going to fight with each other. I see the timing algorithm.
Yeah, it's strobing, but look how many windows you got up. Why don't you kill some of those Malvibe windows? That's a very
Yeah.
big burden on your CPU. I mean, all those pixels going up?
Yeah. Well, that's why I usually kill the, pause it.
If you see it strobing, that's usually what's going on. You can kill apps or you can kill windows.
Yeah.
And that's actual computer term. It's not that we're militaristic. It's a Unix term.
Yeah, the frequencies of all of these phasors should be constant. But you can see 3 is pretty messy. You are talking about the projection of a 6-dimensional space.
Right there.
In 6 dimensions, it's a fairly simple object, but projected on, to 2, at some arbitrary angle, basically, it's not simple at all.
So this is kind of basically the way to visualize higher dimensional spaces.
The beginning of it, obviously, you need to improve on it, because it's really hard to visualize even the 4-dimensional solids with something this crude. You remember those things that we did with a couple of pendulums that were 4-dimensional torus. They had a hole this way and then another hole perpendicular to that. But it never completes because you're leaving out one of the 4 dimensions.
Should we employ a projection technique at that point if we're going from higher dimension to, say, 3? Would that be one of our ways
Yeah,
out? Choose a point in the 4 space and project through it?
I hesitate to say yes because in my experience when I've played with things like that with more than 4 dimensions, no matter how clever you think you are after you've done playing with 4 dimensions, this is crap, I can't see anything. And so you get discouraged. But it might be worthwhile. This is the kind of thing Wolfram has people that worry about stuff like this. And I just wonder if something they've done would help us with many dimensions. I don't know. It may be that it's something that's really hard what to do. What's that thing, a Tabashau Yao sphere or something like that?
I think, yeah.
Google Yao and you'll get it. I think it's something from string theory, and they try to visualize a six-dimensional thing, and they got a couple of things that looked interesting, but it wasn't, it wasn't something you say, oh, that's simple, you can figure it out. It was just remained six-dimensional, and that was all there was to it. And also the Penrose.
The knots, yes.
The Penrose Robertson figure, people have made sense out of that.
Mm-hmm. Okay, that's kind of a motivation.
By laying circles on top of each other.
Exactly. And see how they sort of sit in three space.
So that did work,
Projected.
although we still don't know what it is. Oh, I should ask, can you guys come on a different time than next Tuesday? Al has asked for us to come over and give a talk at the course that's called Teaching Methods or something. And it's being held in the Center for Excellent Turkeys.
Can you email me that and then it'll be locked in?
But it's the same time as this class. That's the problem with it.
Mm-hmm.
So I was wondering, either a Monday or a Wednesday, is that a possibility?
Yeah, I don't have anything like Monday afternoon or Wednesday.
And are you available on Monday afternoon?
Yeah, I have, the last class I have finishes at 3 on Monday.
Okay, so if we did
well,
a 3:30?
actually, I think I have a lab
You have a
until
lab?
6.
Till 6?
Yeah.
Wednesday.
So you've got a class that goes from 2 to 3 or something?
And then a lab in experimental physics, electronics and experimental physics from 3 to 6.
What about Wednesday? Is there any possibility there?
Yeah, Wednesday.
At the same time?
Like from 3:30 to 6. Yeah, I do have time Wednesday.
How about you?
Yeah, I can do that.
Okay, let's make this class Wednesday instead of, that'll be next week. Next week. We'll come on Thursday here, but then the next class after that will be a Wednesday. I'll send an email.
Okay.
Oh, and on that quiz, I tried email. I lost an email list, so please give me your emails. Name and email. Take those. So yeah, we'll do Wednesday, regular time. I have a faculty meeting if I do, screw it.